Welcome to this tutorial on heat transfer. Today we are going to introduce the concept of thermal gradient, which is a key issue when analyzing the heat transfer by conduction. Let's consider this wall. We have a wall with a thickness delta X, and we have at the one side a temperature T1 and at the other side a temperature T2. Due to this temperature difference, we have heat transfer by conduction, which is represented by the Fourier's law of conduction. Then, the heat transfer by conduction is proportional to the conductivity, to the surface, to the temperature difference, divided by the delta X, which is the thickness of the wall. If we reorder these terms, we can introduce this minus sign, which means that the heat transfer by conduction is positive when the delta T, when the difference of temperature is negative, and we can get from this drawing. If we make delta X approach to 0, we get the general form of the Fourier's law of conduction. And from this, we can get the definition of thermal gradient, which is the derivative of the temperature with respect to the distance, in this case x. Then we can define the thermal gradient as the temperature variation per unit of distance. And the thermal gradient causes a heat transfer from the hotter body, from the higher temperature, to the colder one. Prior to continue, we have to introduce some mathematical concepts that are very important to understand what really lies behind this. First of all, we have to consider that the temperature is a scalar quantity. That is, every point in the space has this magnitude, which is a temperature only in value. But when we talk about thermal gradient, we have a quantity, but also have a direction. That's why this is a vectorial quantity. And we can define this thermal gradient as the differential of T with respect to X in the X-axis plus the differential of T with respect to Y in the J-axis plus differential of T with respect to zeta in the K-axis. So we have to consider that in general, the heat transfer is multidimensional. Heat transfer is taking place in 3 dimensions. And this is the typical representation of that. We can see that the temperature is varying in the x-axis, is varying in the z-axis, and is varying in the y-axis. And this is the more general form of the heat transfer that we can refer to as 3-dimensional. Then, a more simplified version of this will be the situation as the one we have in this image, where the temperature is varying in the x direction and also varying in the zeta direction. And we refer to this problem as the 2-dimensional heat transfer problem. Then if we have the variation only in one axis, as for example occurs here in the x-axis, we refer to as 1-dimensional problem. And it is very important to make this simplification from 3D to 2D or to 1D, since the problem is much easier to solve. Considering the specific problem where we can consider the problem as 1-dimensional, we can see that the heat transfer by conduction, when we consider a flat plate, is only dependent on X. If we consider a cylinder, the heat transfer by conduction is only a function of the radio, and the same occurs with the sphere, but in this case the dimension is the radio of the sphere. So considering that specific problem, that is the 1-dimensional problem, the temperature field is only depending on one axis, and the specific expression of the conductivity is equal, as we explained before, minus the conductivity times the surface times the differential of temperature with respect to that significant direction. So if we consider a given flat plate or a wall, what we can see is that if this is the variation of the temperature, for any point we can define the gradient, the thermal gradient. As here this thermal gradient is negative, it decreases with x, we can say that the heat transfer in this case is positive because of this minus sign, as we explained before. So in the opposite case, when the gradient is positive, we obtain that the heat transfer by conduction is negative. It goes in the opposite direction. The same that we are explaining here for one-dimensional heat transfer problem can be applied to multidimensional, three-dimensional heat transfer problem where temperature field depends on x, y, and z. The more general expression of the heat transfer for this case is also minus the conductivity times the surface multiplied by the differential of the temperature with respect to n, and n is the perpendicular direction to the isothermal lines. If we draw here these isothermal lines, we can draw the heat conductivity as something that is perpendicular. Here we will have 90 degrees. And we can decompose this heat transfer in the three orthogonal directions, which can be expressed each of these terms as we made before for the one-dimensional case. So we can conclude underlining the next ideas. First of all, that the temperature is a scalar magnitude. That is, every point in the space has a temperature which is a single value. However, thermal gradient is a vectoral magnitude. It has a value, but it has also a direction. So this is the main difference that we have to consider. Then the heat transfer direction is always contrary to the thermal gradient direction, and we introduced that into the Fourier's law of conduction by this minus sign. Then that the heat flux is in general three-dimensional, so it occurs in the x direction, in the y direction, and in the z direction, but it can be simplified into two-dimensional problem or into one-dimensional problem. And just the last idea I would like to remark is that the heat transfer direction is always perpendicular to isothermal lines.